Hi, this is Kirsten Basset.
This is Joey Ghotmi.
And this is the Kangaroo Crew.
What exactly are we looking for when we run emission spectroscopy?
Well, we're looking for lambda max.
What exactly is a lambda max?
Lambda max represents the wavelength with the largest concentration of emitted photons in a specific substance.
When you record an emission spectroscopy, you receive a peak. The maximum of the peak corresponds with an x value that is lambda max. The position of lambda max on the x-axis represents the wavelength, which in turn represents the color emitted from the substance. What does the intensity represent in emission spectroscopy?
Intensity is the amount of photons being released at a specific wavelength.
So, what is a photon?
A photon is a quantized energy that is released when an excited electron goes from a high state of energy to a lower state of energy.
When an electron relaxes to a lower energy state, a greater difference in energy states corresponds to a smaller wavelength. Because green travels a larger distance, it releases more energy and therefore has a shorter wavelength than the red. The energy that is released from these electrons moving down to the ground state creates photons corresponding to the color of their specific wavelengths. A way to understand energy states is to imagine the electrons existing in these different energy levels instead of traveling to them. The electrons instantly jump from one energy level to another, emitting or absorbing a photon each time.
Photon energizes an atom's valence electron. The quantized energy of the photon promotes the electron into the next unoccupied orbital. After a while, the electron will relax back to its ground state. The energy release is in the form of a photon which correlates to a wavelength. The larger the energy gap, the smaller the wavelength, and the smaller the energy gap, the larger the wavelength. When a bond is made between a hydrogen and carbon atom, the bond delocalizes electrons in between the two atoms, increasing the area of the electron density, which decreases the electron repulsive forces and increases proton-electron attractive forces between the two nuclei. Conjugation, which is the switching back and forth between single and double bonds, is just a fancy word for resonance. When a molecule has resonance, the molecule has an average bond length that rests between a single and double bond. Since the electrons are delocalized around the total molecular structure, it maximizes the total area of electron density, which lowers the kinetic energy of the system. It also maximizes the attractive forces between nuclei of all of the atoms and the electrons that are delocalized, and minimizes the electron repulsion forces since there is more of an area for the electrons to orient themselves, which minimizes potential energy. When an atom becomes excited and allows an electron to move to a higher orbital, the energy jump will be larger than the jump between a single bond and the next orbital, since the electron is delocalized in a space between two atoms and is potentially closer to the next orbital than a relaxed electron would be in a single atom. The same goes for an electron in resonance, but more so since it's delocalized around the structure, giving even less energy to allow the electron into the next highest energy state. Here's an analogy to help us understand the nature of these bonds and resonance structures. If a mom and her child are hanging out at a park, the mom will lay down some ground rules as to where the kid can go, since she's only comfortable allowing him to roam a certain amount of space. But the kid really wants to go to the purple area since there's a really cool toy over there. However, he'll get into a lot of trouble if he does this, since his mom only has enough energy to watch him in the black circle. Now let's say the kid's aunt and cousin come to play at the park too. Aunt has her own scope around her own child as well, but when she forms a bond with the mom, they can watch a larger space between the two of them. The kids are able to play in the space between the two parents, which also allows them to go to the purple place more easily. A resonance structure can be thought of as a family gathering. The kids can play in a lot more purple areas than they could have before because they have a lot more adults around. When comparing green and orange dye molecular structures, the only difference is the added resonance carbon chain on the bottom of the orange structure. As expected, the green dye has a smaller wavelength and requires more energy than the orange dye. The red dye is more complex of a structure, containing more than just carbon and hydrogen atoms. Electrons would be easier to localize in a CC bond than a CO bond, for instance, because the electrons are evenly displaced among the carbon atoms. In the CO bond, the electrons surround the oxygen more because it is more favorable to be around the higher proton atom. This reduces potential energy in the bond, which also lowers the potential energy of the entire red molecular structure. Why are there two peaks on the graph?
There's two peaks on the graph because both the green dye and the red dye have different lambda maxes, which is their differentiating characteristic based on their molecular structure. Now, in our experiment, the green dye had a lambda max at 504 nanometers, and our red dye had a lambda max at 614 nanometers.